Hi again. We are picking up with the rest of Chapter 1 now, sections 1.5 through 1.7, which is linear inequalities and absolute value equations. So we're going to start with linear inequalities in one variable. So an inequality has a less than or a greater than sign in it somewhere. And so there are lots of different options. There's one big chart that you can look at if you want to. That's this chart here. It's also in the book. But we're going to do most of these different combinations here in this next this section and the next section. So we typically want to write our solutions in what is called interval notation. And so interval notation, that's this third column here. That's what we usually write it in. That's where we write numbers or infinities with parentheses or brackets. On your homework, you'll notice they'll ask for interval notation, and they'll also ask you on occasion to graph it. And so I'm going to be doing both of those. The set builder notation is kind of what you're going to end up with when we actually solve it out. You'll end up with something that might look like, say, this part right here, where x is greater than a, or x is less than a, or x is greater than or equal to a, or x is less than or equal to a. You'll end up with one of those type things. We will then transfer that over to make it look like one of the options in the interval notation. And so if you have x is greater than a, you'll end up with writing a to infinity. Or if x is greater than or equal to a, you would put a bracket on the a. Or if the other way around, x is less than a, you'll go negative infinity to a. Notice the infinity, if you treat the infinity, if you treat the less than or greater than sign as the tip of an arrow, it will point toward the direction that the graph goes, and it will also point toward the infinity. So the infinity would go on the right-hand side or the left-hand side, depending on if it's greater than or less than. So that whole chart you can sum up in a few different sentences. If there is an equal to sign, we'll use closed circle or brackets. This book uses brackets on the graphs, but that's the same thing as closed circles if you've seen that in a different course. Or open circles and parentheses would be used if it does not have the equal to sign on it, if it's strictly greater than or less than. Infinities, either positive or negative, always have parentheses. You never put a bracket on an infinity, either positive or negative. Always parentheses. And solving an inequality, a linear inequality, uses the same rules that we did at the last video for linear equations, except if you were to multiply by or divide by a negative number, you have to swap the inequality around. So the less than would become greater than, or the greater than would become less than. So let's do some problems. Those 4 steps that we talked about on the linear equation still apply. If you have a fraction, you get rid of the fraction first. No fractions on any of these 3 problems, so we don't worry about that. Second step, simplify if you can on either side. Here, again, no simplifying needed on the x minus 7 or the negative 12. So we go to the third step, try to get the x by itself. So in this one, this first one, I can add the 7 to both sides. And your less than would be treated just like your equal to. So if you want to draw a line through that, like what we were doing in the last video, like this, you are welcome to do that. And you'll end up with x is less than negative 7 plus 12 would be negative 5. So this would go back to the chart where you had x is less than a. This would be your set builder notation, but our interval notation would say that this goes from negative infinity to negative 5. parentheses on everything, because there's no equal to. And your infinity goes on the left because it's a less than. You could also think of it as the parts with the L's go together. Less than, left-hand side for the infinity. Or you could look at it as an arrowhead. The arrowhead idea, if you were to graph it, would say I would go to -5. I would put a parenthesis or an open circle, and it would be everything to the left. It might be easier for me to do it as a highlighter instead. I don't know. We'll try it on the next one. On the next one, we have 5x is less than or equal to -30. Here, there's no fractions, there's no simplifying, and in fact, the x's are already on one side and the numbers on the other, so we can skip all the way to the last step, where all I really have to do is divide by 5 on both sides. Now notice you're dividing by +5, so +5 will not change anything. It will stay less than or equal to, and this becomes -6. It's almost identical to the first one, except for the equal to part. So this one would go -infinity to -6. The -6 ends up with a bracket on it. Remember, the infinity never gets a bracket. Never gets a bracket. But the -6 does. And so if I was to draw that out on a number line, I would go with -6, and I would do everything to the left. And since it is a equal to, or a bracket, I have a bracket at -6. Not a parenthesis. Or you could also see it as a closed dot. Now on number 3, you have a little bit of work to do. If I was to divide this one down the middle, you would notice that on the left-hand side, you got a lot of simplifying to do. We have a -3 that needs to be multiplied across, and then we'll also have to combine it with a 2. But the 7 minus x on the right-hand side is perfectly fine the way it is. So this will become -3x minus 12 plus 2. The -12 and the 2 can go together as -10. And then you have the left-hand side simplified. Then we got to move all the x's to one side and all the numbers to the other. So I would add the x to the left-hand side. And if you want to do it in multiple steps, you can. You can add the 10 as well as you go along. If you don't want to do it in multiple steps, that's okay. But then that'll cancel the x's and the 10's and leave me with -4x. And 10 and 7 make 17. Ooh, this will not come out very evenly, will it? Oh well. And then if I was to divide both sides by -4, notice here I'm dividing by -4. So if it's negative when you multiply or divide, you have to swap the inequality around. So this will leave me with x is now less than, not greater than, less than -17/4. So it's actually the same as the first one. The less than, not less than or equal to, but just less than, would tell me I would go from -infinity to -17/4. Parentheses everywhere, since it's not an equal to. And by the way, a lot of the times on the homework, you won't see 17 divided by 4 on the number line. The number lines will just be multiple choice for you to pick from, but you won't necessarily see 17/4. What you would probably see is -4 and -5. 17/4 is 4.25, So you would end up with a parenthesis starting somewhere about here. That would be 17 over 4, and then we would fill in everything to the right. So you may not see that particular fraction on there. Okay. Number 4. We have 10k minus 3 over 3 is greater than 3. Again, here we have a fraction. So if you have a fraction, the first thing you want to do is get rid of that fraction. So I'm going to multiply everything in this problem by 3. Now the 3 that I'm multiplying by is positive, so that will not affect the inequality sign. This 3 will cancel this 3 completely and leave you with a 1 left over. That 1 gets multiplied times the stuff on the inside. And we kind of did this process already. And so this will just leave me with a 10k minus 3 is greater than 9. At that point, I don't have to simplify one side or the other, so I can just add the 3 to both sides of the inequality. And I will get that 10k is greater than 12. And if I were to divide by 10 on both sides to get the k by itself, I would end up with k is greater than 12 over 10. But 12 over 10 can simplify. You can divide each one of those by 2 and say that this is actually 6 over 5. So being greater than 6 over 5 tells me I'm going from 6 over 5 to infinity. So that would be your interval notation. Remember, the inequality is pointing to the right, so the right-hand side would have the infinity. Positive infinity always goes on the right. Negative infinity always goes on the left. And then if I were to graph that, just like on the last one, 6 over 5 is probably not going to be on the number line. So you'll see the number 1. You'll see the number 2. 6 over 5 is 1.2. So you would probably see a parenthesis just a little bit to the right of 1. And then we would just fill it in as we go to the right. Now those first 4 examples are all examples of linear inequalities. 5 and 6 are examples of actually what we call compound linear inequalities. Compound because there are actually 2 inequality signs in the problem. 3 is less than x minus 2 is less than or equal to 8. You do all the same process, but you try to get the x in the middle by itself. And so this one's fairly easy to do. I could add the 2, but I have to add the 2 to 3 different portions. And so I would get that 5 is less than x is less than or equal to 8, and 2 give me 10. If you look back on that chart, this is one of the options. If you have an x between 2 numbers, then your interval notation is just those 2 numbers. You would write the 5 and the 10. The 5 gets a parenthesis. The 10 gets a bracket. The 5 gets a parenthesis because there's an equal, not an equal to on the less than. It's just strictly less than. But next to the 10, it's less than or equal to. So that equal to tells you to put a bracket on there. And so I'll put a bracket on the 10. When I graph this one, I would have the 5 and go 6, 7, 8, 9, 10. I would have a parenthesis or possibly an open circle on the 5. I would have a bracket or a closed circle on the 10. And I would have all the stuff in between. Now, number 6 is a little bit more complicated, but it's the same sort of thing. You want to try to get the m by itself in the middle. So what we do is we multiply everything times 4. So everything times 4. The 2 gets multiplied by the 4. The 10 gets multiplied by the 4. And we're multiplying by 4 because that's what's on the denominator, the bottom of that fraction. So the 4's will cancel. And so I'm left with negative 8 is less than or equal to 3m plus 1, which is less than or equal to 40. Then to get the m by itself, I need to subtract 1 everywhere. So if I subtract 1, and subtract 1, I'm going to have to write this kind of up here somewhere. If you subtract 1 from both sides, you'll get negative 9 is less than or equal to 3m, which is less than or equal to 39. And then to get the m by itself, we divide everything by 3. Notice the 3 is a positive value that you're dividing by, so it will not change the sign. And we'll end up with negative 3 is less than or equal to m, less than or equal to 13. So it's very much like number 5, except here 2 numbers have brackets on them because they both are less than or equal to. So I'll have a interval notation of negative 3 to 13, brackets on everything. And my graph's going to be kind of small because I'm about out of room on this page. But I'll have a negative 3 and I'll have a 13. There'll be brackets on both of them. And we do the stuff in between. Now, technically, these last two problems, 5 and 6, should have probably been in the next section in this book. I'm not sure why they're not. But the next section is actually called compound inequalities, and that's what 5 and 6 actually are. So speaking of compound inequalities, a compound inequality is where you have multiple inequalities in one problem. There are 2 types. There's the AND compound inequality, which has to make both inequalities true. And there's the OR compound inequality, where one or the other one could be true. They don't both have to be true. The AND compound inequalities usually look like what we just did, where you have something less than or equal to x less than something. That would be a compound inequality with an AND, because you're saying x is less than 10 and x is greater than or equal to negative 5. An OR will literally have the word OR in between them. You might see it as x is greater than 10 or x is less than 5. So those are pretty easy to pick off. And compound inequalities will have the interval notation between the 2 numbers. It'll go negative 5, 10. Or compound inequalities do not. They will have an OR will get turned into a union symbol, which will have a U. X is less than 5 says we're going from negative infinity to 5. And then x is greater than 10 says I go 10 to infinity. So it'll look like that when you get done. Now, sometimes they do stick the word and in between there, but you could rewrite it the other way. X is less than or equal to 3 and x is greater than negative 2. This is literally saying the same thing as negative 2 to x to 3. They mean the exact same thing. And so if you see an and compound inequality, this one's already solved. We don't even do anything with it. We're just going to go with the 2 numbers. We'll go negative 2 to 3. The 3 gets the bracket on it because of the equal to. The 2 gets a parenthesis. And we will graph it by putting a bracket on the 3 or a closed dot and a parenthesis on the negative 2, or an open dot if you want to do the open dot. And it's the stuff in between. Your and inequalities are always the stuff in between. Your or inequalities is the stuff on the ends of your number line. So on this one, you'll notice it's an or inequality because it kind of gives it away with the whole, or right there. But you solve each one of them independently. So on the first one, I would subtract the 3 from both sides and say that x is less than or equal to 6. I would solve the other one by dividing by 2 on both sides and say that x is greater than 9. And so less than or equal to 6 says I go from negative infinity to 6 with a bracket. X is greater than 9 says I go from 9 to infinity. Parentheses on everything there. And the word or gets turned into a union symbol. This is how you will write or compound inequalities. Graphing it, you just end up with the end parts of your number line. We'll have a 6 on there, we'll have a 9 on there. The 6 has a bracket on it, but the bracket faces away from the 9. And the 9 has a parenthesis on it facing away from the 6. And we do everything bigger than 9, which goes this direction, or less than 6, which goes that direction. So your ors are the ends of your number lines. The ands, compounding inequalities, are the ones that are in between two numbers. Okay, these are two more, another and another or. Again, you could write this first one, since it's 4 is less than 3x plus 1 and 3x plus 1 is less than negative 5. You could write it by combining the two together. If you don't, it's perfectly okay. But the 3x plus 1 had to be less than negative 5, but it had to be greater than 4. You might notice that's not possible. You can't, if you pretend that 3x plus 1 is just a number, is there a number that's bigger than 4 but less than negative 5? And the answer is no, you can't be less than negative 5 and greater than 4. But pretend like you don't notice that. Let's see what happens if you solve it. If you subtract the 1 from both sides to try to get the x by itself, you'll get that 3 is less than 3x, which is less than negative 6. Then I would divide everything by 3 and get that 1 is less than x, which is less than negative 2. So it would look like, well, I would go from 1 to negative 2, right? But you can't do that. This is not possible because you're going always from a lower number to a higher number. Negative 2 is a lower number than 1. So you can't do that. Or if you looked at it on a graph, you would want to do 1 and then negative 2. But negative 2 is not to the right of 1. So that doesn't work either. So in this case, there is no interval that will make that work. So this actually is the empty set or no solution. So we could write it with an empty set. There's no set, there's no interval that would make that work. Or there's no solution, whichever one you want to put. That does happen on some and ones. Some or ones actually end up being everything. So you get it kind of the other way around. So on number 4, if I was to subtract the 7 from both sides, I would get that x is greater than 10. On the other one, if I was to subtract 10 from both sides, I would get that negative x is greater than 12. 22 minus 10. But I don't need negative x, I need positive x. So I have to divide by negative 1. And remember, if you divide by a negative, you swap the sign, so it becomes less than negative 12. And so the less than part always goes first. x is less than negative 12 says I go from negative infinity to negative 12. Or becomes a union. And by the way, the union is not the U on the keyboard. It is one of the, across the bottom, there's a palette to use. There's one that's a U and one that's an upside down U. Don't ever pick the upside down U. Always pick the U one. And greater than 10 tells you to go from 10 to infinity. If you were to graph that, we would go from negative 12 and 10, putting those on the number line. The 12, since they all have just parentheses, you'd have an open parenthesis facing to the left, and on the 10, you'd have an open parenthesis facing to the right, and we would go the endpoints. Ooh, didn't mean to do that. And that would be your answer. Okay, the last thing in this video that we'll be talking about is absolute value equations. We will not do absolute value inequalities, for some of you that may remember that from a previous course. We don't do inequalities in this class. They do absolute value inequalities in college algebra. But in intermediate algebra, we do not. So we're only going to do the equations. So if possible, you got to get the absolute value bars by themselves. Then whatever's inside the bars is equal to what you're given and the opposite of what you're given. So for instance, if you had the absolute value of 2x plus 1 equals 3, I would make it be 2x plus 1 equals 3 and 2x plus 1 equals negative 3. So you make it what it's equal to and the opposite of what it's equal to. Please notice though, if it said 2x plus 1 equals negative 3 though, you don't do that. The negative on the 3, your absolute value can never, ever, ever be negative. So if there's a negative right here, is that equal to a absolute value equation? The answer is always no solution. Always. That's one of the easiest problems that you'll see on the homework. So let's do some. So for instance, the first one, the absolute value of x equals 4. That means I take what's inside the absolute values, which is the x, and I set it equal to 4, and I set it equal to negative 4. In this case, you're done because you already have the x's by themselves. That was easy, right? On number 2, I would take what's inside the absolute values and set it equal to 6, and set it equal to negative 6. And then you solve each one of those by getting the x by itself. We subtract the 1 everywhere. And so I'll get that either x is 5 or x is negative 7. These also, you can plug them back in and make sure they work. If you did 5 plus 1 back in the original problem, you'll get 6. The absolute value of 6 is 6. And number 3, that's the one that I was telling you about earlier. There's a negative sitting right there. You have an absolute value equal to a negative number. There is no work to do on this. There's absolutely nothing to write down. This has no solution, because you cannot have an absolute value equal to a negative number. I like those. Now, if your absolute value is not already by itself, you do have to get it by itself before you split it up. So for instance, on this first one, absolute value of y minus 3 minus 11 equals negative 6. Some people look at the negative 6 and say, oh, well, there's a negative on the right-hand side. There's no solution. That's not the case if you don't have the absolute value by itself. So we do have to add this 11 to both sides before I begin. And so I'll have the absolute value of y minus 3 equals 11 minus 6, which is 5. Then I can actually split it up. I'll either say that y minus 3 equals 5 or y minus 3 equals negative 5. Add the 3 to everything to get the y by itself. And you'll get y equals 8 or y equals -2. And again, you can check it if you want to. If you plug 8 in, 8 minus 3 is 5. 5 minus 11 is -6. So yeah, that's right. Now, it is possible to have absolute values on both sides. Now, in that case, what we'll do is we do the same thing where there's no rearranging here like we did on number 4. You just have to jump in and make two equations. You'll either say that 3x plus 10 equals x minus 17, or you say 3x plus 10 is negative x plus 17. Just like with the 5 up above it, I made the 5 positive 5 on one equation and negative 5 on the other equation. Here, I take one side or the other. I'll take the right-hand side, and I leave it the way it is, x minus 17. And on the other equation, I make it the opposite of what it is, negative x plus 17. And then you just solve it like we've been doing all the other problems. I would subtract the 10 from both sides. And I'll end up with 3x equals x minus 27, or 3x equals negative x plus 7. Then I get the x's together, so I'll subtract the x here to get 2x equals negative 27, or on the other one, add the x to get 4x equals 7. And then divide each one of them. I'll divide the first one by 2 and the second one by 4 to get the x's by themselves. And I'll get that x equals negative 27 over 2, which is a little harder to check if you do want to check it, or x equals 7 over 4. Those didn't come out quite as nice, but it happens. But on the absolute value equations, you're usually looking for two answers. And you'll notice we got 2 answers on every one of them. So hopefully that makes some sense. That's the end of chapter 1. And so after this, we'll start chapter 2.